original Hawking's calculation to get the thermal spectrum that he got for a black hole. In my case, it's going to be a Schwarzschild black hole to keep computations simple. This is the metric that the Schwarzschild black hole takes in form, where PR is 1 minus 2gm by using natural equations for G, where G is 1. We then converted, we did some coordinate transformation to have it moving from a Schwarzschild metric to a Mishal's coordinates, where Schwarzschild metric is only is okay for a finite manifold, but the Mishal's coordinate is like for infinite amount of spaces, which we will need to solve Hawking radiation, where he takes his calculation sort of back in time. He calculates for rays propagating back in time. Where the
use the highlighter.
These are the crystals. Where U and V are ingoing and outgoing null crystal coordinates. And also, I define the radial part in tortoise coordinates such that it takes the form. Takes the form such as as you can see, it took that form. And I should also, it's really sorry, I should also look into the mass speed of fusion. This is a solution for the mass speed of fusion, which then, if you try to solve for phi, which would have been a phi operator, then I'm really sorry, we do a separate. To solve for phi, we use the separable solution formula to get the radial part, to get the radial, to reduce it to this format. Hawking's original calculation were done in gravitational collapse spacetime, where star was basically is basically collapsing, and therein a Hawking particle is being radiated. And in the far, he's as I mentioned before, he's doing his calculation. We're going to go back in time, our photon, so to speak. Particle, so to speak. Wherein in far past, spacetime is nearly Minkowski. We assume at null infinity, past null infinity, state 0 in state, which obviously should be devoid of particles, since the particle creation hasn't occurred yet. Subsequently, the star then will collapse into a black hole. We state then, after it has collapsed into a black hole, that this state will have now a thermal flux of particles. Obviously, because of particle creation, which Hawking explained in the last slide, the last lecture. To define particle states in far past, we must choose a set of basis function. And since our I minus is a Cauchy horizon, we can then have a positive set of frequency solutions, which will map like f omega uv is e to the power minus I omega v, where v is an affine parameter for the null geodesic generator at past null infinity. Where now we can solve for the field at past null infinity with this expansion, where this is the solution that we saw before for positive frequencies, and we're working here for positive frequencies. This is going to be positive frequency, only positive frequency. A omega here is an annihilation operator, and A dagger is a creation operator. Sorry.
And this is not the complete set of solution. We need complete set of solutions for H plus and I plus, where H plus is the black hole horizon, and I plus is positive null infinity. But the issue here is I plus is not a Cauchy horizon. So it's not a Cauchy horizon, but I'll get back to that. For I plus, just sort of like I minus, we take the out stage two solutions to the wave equation, where here again P omega is equals to e to the power minus I omega u, where u is the null geodesic operator. To form a complete base, we must define positive frequency mode zone H plus and its extension to collapsing matter. Previously, before, we sort of chose space-time where in past null infinity and future null infinity, the space-time is basically sort of flat, but in H plus, which is near the horizon, it's not flat. We have to take curvature into account. We choose a specific set of Q modes, the QW, that are sort of well behaved in this near the horizon. And obviously, it's logically understandable that the system be a pure state for which the density matrix is as follows. And I'm pretty sure you got a taste of density matrix when Rakin did this previous lecture. Expanding rho now in H plus and I minus, we get the scalar field in the out basis, where it's a summation of all these. These are the creation operators. Creation operators acting on Fock space H plus and Fock space I plus. We consider a wave packet. See, when a black hole starts radiating particles, there are particles that scatter out through sort of flat space and basically scatter in towards the black hole. For Hawking's calculation, he basically ignored the particle that scatters sort of outward and only takes into consideration the particles that are sort of starting to come in. And this, mind you, the black hole hasn't fully formed yet. The star has started to just collapse. Here, that's omega. This is the amplitude which propagates parallel to H minus, which is the white hole horizon, and subsequently absorbed by the horizon. I forgot to mention these alpha omega omega prime and beta omega omega prime are Bogoliubov coefficients. As I said so before, Hawking's original calculation was done by studying wave propagating backwards in time in the collapsing space-time. We must then figure out what occurs to the scalar field phi on I minus. We have arbitrarily chosen our frequency to be positive, but on I minus it could be a combination of positive and negative frequencies. We want to see what occurs there. And yeah, we want to try to calculate Hawking radiation, the extent of short-shell spacetime, so as to get a black body distribution that he got in his original calculation. We have a mode that mode P e to the power minus I omega, which, as you might remember, was at positive null infinity, propagating backwards along a path gamma that goes along a geodesic u is equals to u1, 2v is equals to v1, which can approximately be taken to v0. Here, gamma is connected to the black hole horizon by a geodesic deviation vector epsilon n to the power a, where epsilon is always positive and infinitesimal. And on the part that is close to H plus, Na is tangent to the null geodesic ingoing at H plus, which is the black hole horizon. As you can see, I drew a Penrose diagram there, where you'll see where all the white hole horizons are and the black hole horizons are, including positive null infinity, null infinity and null future and null past. We have also normalized the tangent, where NALA is equals to -1, and LA is the null geodesic generator of H plus. Sorry, that's a typo. We have PA to be a tangent to an ingoing null geodesic at the horizon, which is denoted by the operator. where PB is equals to A square and B. Now I want to basically state what I'm trying to do here is try to find a relation between U and B, where U and B are solving the geodesic equation near the black hole horizon. We get the affine parameters in terms of U, where the affine parameter lambda is equal to minus b squared e to the power minus kb, where U is the crystal. And here in local inertial coordinates, the geodesic equation basically delves into lambda b mu is equals to minus epsilon n mu. And as you can see by these two equations, equation 16 and 18, we shall then find a relation for epsilon. We get a value for epsilon is equals to minus lambda a squared. Now we trace gamma through a collapsing star and back to I minus. Remember, where I iterated before, it's going back in time through the collapsing star and back to past null infinity. And this is unpredictable self-explanatory. And as you can see here, what we're trying to find is a relation between V and U, and we have found a relationship. Fixing boundary conditions to solve the scalar wave equations at past null infinity. We have phi is equals to e to the power, and if we solve the equation there, phi is equals to e to the power minus I omega kappa. Here kappa is the surface gravity of the black hole, and this is for V less than 0. You get a solution for phi for V less than 0. For V greater than 0, it just gives absorbed to the black hole. Expression the Bogoliubov coefficients does look like this, and we solve it to find beta omega omega prime is equals to minus I alpha omega omega prime. Because the Bogoliubov coefficients alpha omega omega prime is only analytical in the lower part of the half of the complex plane, we have alpha omega omega prime is equals to e to the power pi omega kappa beta omega omega prime. And thus, finally, we get to calculate the spectrum of radiated particles, which we then, that's the number of particles that we're supposed to get from Hawking radiation. Integrating, we get this black body spectrum. This black body spectrum, when you compare it to any other black body spectrum, would give us the temperature, which is T is equals to h bar kappa by 2 pi. And here you go, you found the temperature of Hawking radiation. Now I shall go into the non-thermal radiation, go into some another model. Rakin proposed small correction models, which, if I heard it correctly, almost all of them failed. Yeah. So this was proposed by Wilczek, who proposed that there should be some tunneling effects of the particles that go inside the black hole. There should be some tunneling dynamics that cause it to have correlations between the particles that have already gone out. These correlations will then decrease the black hole information. Will then cause us to not have any information paradox. As Joan Bai said before, why is there an information paradox? And as you can see, if the black hole basically decreases, evaporates away, it'll become a small Transplanckian remnant. And as it becomes a small Transplanckian remnant, what happens to the entangled entropy term? You're losing your information right there. But if you get all that information out via entanglement through non-thermal radiation, in the previous calculation we calculated for we got a thermal spectrum, wherein there's always a temperature term. We got a sort of quasi black body spectrum. Black was not a pure black body, but we got a quasi pure black body spectrum which gave out thermal particles away. But here we'll actually do the calculations for non-thermal particles that might be radiated away from a black hole. Well, I wanted to add that we call the term hairs. These hairs are inherent properties of the black holes In these calculations, we don't really need the way the way the author calculated this. He didn't even take into account tunneling dynamics. He just used the properties of the hairs and the Hawking-Bekenstein entropy formula. Where they use the Hawking-Bekenstein entropy formula, which is linked to the area of the black hole. And obviously, as I said so before, the spectrum allows for correlations between subsequent particles, and when calculated, information is conserved. As Rakin said before, like for the page curve, correlations sort of started taking it at the halfway point, basically. If n particles eventually come out of black holes, then page curve decreases the entropy after n by 2 particles. Here it basically starts instantaneously. But see, the calculation for the thermal spectrum is it was an approximation where the energy of the particles that have been radiated away are so high that it dwarfs the non-thermal spectrum. Which is why in previous calculations we got the thermal spectrum. But if you consider high energy of the particles that have produced and gone away, then you start coming across the non-thermal spectrum as well. I have drawn here a crude arbitrary diagram where the whole thing is the universe, and this is your environment O. This whole thing, say for example, is a young star that has just been collapsed. This B prime is a black hole that has started to evaporate away. This would have been B, but nothing really lasts forever and starts evaporating. And here, R is the radiated particles that are going away. This is a relationship. I'll come across this a lot from my calculations, that's why I just drew it. We assume that the universe to be an arbitrary pure state. Where is the state? This is the state of the black hole, the gas product with the state of the environment, and C here is just the coefficient. And gamma U is the total number of microstates for the universe with energy EU of the total universe. We find the normalization of the psi, which is this is equal gamma B, gamma O is 1, where we also find the average value of the coefficient, of said coefficient to be 1. As we do some mathematics, we define for a black hole state psi B is equal to psi B to be sigma O, CBO, and as you also saw before on the Rakin's lecture, we work with reduced density matrix, where we ignore the environment O, and get our density matrix for the black hole to be 1 by gamma U. The average over a large enough subset of O of U is the same as that over U. So we sort of take into approximation that our O is basically our U. It's large enough. We again do some math. We stated what EO is, EU minus EB, and we stated that we say the density matrix in terms of that. We take the energy of the black hole to an arbitrary value E, so and the number of microstates of the black hole is defined that way. Gamma U by gamma O, EU minus E, which is fully contributed by degrees of freedom that degenerated in the macro energy state of B with eigenvalue E. And thus, the reduced density matrix thus finally looks like this. wherein it is dependent on the number of microstates of the black hole. As you can see, this is a microcanonical. This looks like a microcanonical ensemble, wherein we have now the freedom to write it in terms of the original definition of entropy, which is S is equals to ln omega b E. Again, we restate the density matrix where E is the energy of the black hole, as I stated so before. This black hole, which is before it evaporated, minus the energy of the radiated terms that are minus the Hawking radiated terms. Actually, it's not just Hawking radiated. It's not. See, R. We haven't really stated anything. We haven't stated whether R is a thermal particle or a non-thermal particle, so to speak, I guess. We haven't stated what R is yet. We decided to stick to some nomenclature where we reduced R, we take a trace of B, and here you can see delta. We substituted E here. We basically used this formula to restate it in terms of the entropy of the black hole. And we get the reduced density matrix in terms of entropy, basically, entropy of the black hole. Entropy of the black hole that is reducing because of evaporation. And there was one thing that in Wilczek's calculation that they said was, see the Hawking thermal spectrum which comes out, the thermal spectrum that comes out, it is first order where ER, these are linear terms as you can see. But if expanded into higher order, in linear terms you get a thermal spectrum, but if expanded into higher order terms you basically get a non-thermal spectrum. And now we get back to hairs, where we have the state, we have mass is equals to n, which is denoted by the frequency. We have charge, and we have angular momentum. These are the inherent properties of the gravity. If you choose your black hole to have, if you have a black hole that has mass, charge, or angular momentum. And I use Hawking-Bekenstein's formula for entropy, wherein for our black hole, singularity radius is 2RH. So
but you use a different n.
we have done that specific for a black hole which has a singularity to RH. We get the entropy term and the Einstein-Bekenstein entropy term to be pi r squared h, which is the substitution that we did here. For that specific entropy, our calculations are not dependent on tunneling dynamics, but dependent on the entropy of the Hawking-Bekenstein entropy term for specific black holes. Now, different black holes might have different entropy terms with regarding to the horizon radius. Here we again I chose a Schwarzschild black hole so as to make the calculation easier. So in a Schwarzschild black hole we sort of don't take into account charge or angular momentum, just mass term here. And doing the calculation, for here if we do the calculation, we get our non-thermal spectrum. This is our non-thermal spectrum. What would have been, this is the non-thermal spectrum, and this is the probability of state omega being in the distribution, and this is known as particle Wilczek spectrum. What would have been a thermal spectrum, which is rho r is equals to sigma e1 minus 8 pi omega, we have this. as you can see, if you take into account higher energies for radiated particles, we get not just a thermal spectrum, a non-thermal spectrum, which starts to give correlation and thus decreases the entropy and causing entropy to be conserved, hopefully. Any questions?
Okay, yeah. So, considering this non-thermal effect, does the entanglement entropy go down? That right?
Yeah. So it's like information is basically being tunneled out. So the issue is basically, say you have a black hole. Particles being you create two particles. You can't create you can't have odd number of particles by the way. You can only have pairs. So you make pairs. One particle will obviously go in, one particle will go out. And as I said so before, as you add more mass terms into the black hole, it sounds redundant, but it actually starts to decrease the black hole. It decreases the mass of the black hole. So the black hole starts to shrink. And the black hole starts to shrink and it takes a long time, 10 to the 67 years for an average black hole. Okay. So it starts to decrease, but the issue is, once it starts to decrease to a Transplanckian level, you lose that entropy term. So there are many ways to go against it. There was Preskill's way, where he basically states that the particle that goes in gets bleached out of all the information by the horizon, and basically the space-time eats up all the information. That is what I think Mauser knows best about it, information theory, where in space-time will actually start to store the information. So you're losing black hole mass because of the mass of the particle that goes in, but the information stays conserved via spacetime. Here, they use tunneling dynamics where you cause correlations. You added correlations later after the particle being tunneled out, the information being tunneled out, and therefore started to decrease the entropy itself. The more the particles that go up, the more correlation, and it starts decreasing until the black hole is basically Transplanckian remnant, where you don't really need. So you don't have information basically conserved. Yeah.
So, a viewer wants to know if you can observe Hawking radiation from a strong magnetic field in the vacuum.
I don't know how to answer that. I don't know how to experimentally observe Hawking radiation.
Hawking radiation from a magnetic field in a vacuum.
It has to have then it could be a chargeless. It could be a chargeless particle that has been created.
Right, people are trying to make these hydrodynamic black holes. They're Steinhauer or whatever claims to see Hawking radiation. And,
Claims to have seen.
yeah. I'm not sure whether it's debunked or not.
Any other questions?
It's in Nature or whatever, so there's some claim.
Yeah, he's saying theoretically, can you see Hawking radiation from a magnetic?
I mean, you can see Hawking radiation is basically anytime essentially you have two vacuums. It's like a Sanders space-time. You have some vacuum state, stuff happens, another vacuum state. But a more general kind of like description of that is just some sort of metric which is curved or changing or something.
Any other questions?
Can you describe what's going on in this diagram?
This Penrose diagram basically states the beginning of the black hole and the depth of the black hole. Right.
Yeah, how? Please explain.
Here, regions 1 and 3 are asymptotically flat, where there is no black hole. And then the star collapses here and then creates the black hole there. Where you have positive null infinity here, and negative, future null infinity here, and past null infinity there. This is a Penrose diagram.
And what is it? H minus H plus?
Oh, this is H minus this is a white hole horizon. This is as I said so before, it's black hole horizon.
That's a macro singularity.
Mm-hmm. Yeah, that's the next.
People, don't be shy. Anything else? Sir?
Lucky to be here.